Hi, in this video we're going to learn how to prove a statement by handling every possible case. In maths we try to prove statements for all possible numbers. The more general the statement, the better. However, although we're dealing with infinitely many numbers, sometimes we may have a finite number of cases. So let's see this in an example. Prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. Now, we are talking about all square numbers, but the cases we have seem to be finite. Now, we're going to show whether they are multiple of 4 or one more than a multiple of 4. Now, if it's a multiple of 4, then it's an even number. If it's one more than a multiple of 4, then it's an odd number. So I can start with this. I have two options. Numbers can be even, which I could express them as 2n for n being an integer, right? Or let's say a positive integer if you'd like, but it doesn't matter. Or you can say odd, which is 2n plus 1, again for n being an integer. So if I try to get a square number which is even, so let's calculate that, that's going to be 4n squared, and obviously 4n squared is divisible by 4, so this implies it's divisible by 4. So that's a tick. So even square numbers are good. For odd square numbers, when we take the square of 2n plus 1, we end up with 4n squared plus 4n plus 1. And you can write this as 4 in brackets n squared plus n plus 1. So as you can see, this part is a multiple of 4, and altogether it is one more than a multiple of 4. So this is also a tick. So you can say it's shown. Or you can say, QED, right? So just working on two cases, we proved the statement. Now sometimes the numbers you are supposed to deal with could be finite as well. So you can just try them out and show that in each case it fits in. So you can prove it like this. Now let's look at this example. It says prove that the sum of two consecutive square numbers between 100 and 200 is an odd number. So basically we are talking about here 121, 144, 169 and 196, which is 11 squared, 12 squared, 13 squared and 14 squared, right? So it says consecutive square numbers, so I will first consider 121 and 144. If I add them, I get 265. So it is an odd number. Tick. Next, I have 144 and 169. Well, this will add up to 313. Again, an odd number. Tick. And we have now 169 add 196. Now this will add up to 365, which is an odd number. Tick. Now this is what we mean by exhaustion. We use up every possible number, every possible case, and we show that in each case what is asked is proven, right? So here we try the first two square numbers, we end up with an odd number. We tried the next two, and then we ended up with an odd number. And we tried the last two, and we ended up an odd number, right? So what I'm saying is in all cases we ended up with what is asked for, right? So this is the way I prove this statement, proof by exhaustion. right? As you can see, if you have a finite number of cases, then you can use this method and you can suspect that proof by exhaustion is the true method if you are given restrictions like numbers between 100 and 200, right? So sometimes, as in the first example, it's infinitely many numbers, but the expression of these numbers like even and odd, so it's finite. But sometimes, or most of the time, let's say, it is a restriction accompanied with the statement, so that you can figure out there's a finite number of numbers, so there's a finite number of cases, right? So you can just check each and every one of them, so exhaust them, right? And show that the statement is true for every one of them, right? That's the way. Another example, prove that n plus 1 brackets cubed is greater than or equal to 3 to the power of n for positive natural numbers which are less than or equal to 4. Well, first of all, let's find out what this means. But obviously, we are talking about natural numbers and we are talking about positive natural numbers, so 0 is not included. And we can go up to 4 only. So basically, n could be 1, 2, 3, and 4. So instead of thinking other ways like deduction or anything else, we can just consider, just because there are 4 possible values, we can consider substitution. So we can say for n equals 1, 1 plus 1 cubed is, well, we're checking, so we put a square, we put a question mark on top of it, so it's going to be 3 to the power of 1. What happens here is it is 2 cubed, right, and right hand side is 3, so basically we have 8 is greater than 3, which is a tick. So for n equals 1, we're good. For n equals 2, 2 plus 1 cubed is greater than 3 squared. Well, we'll find out. This is 3 cubed we're talking about, and this is 3 squared. Obviously, without calculation, that is correct. Now, for n equals 3, that's going to be like 3 plus 1 cubed is greater than or equal to 3 to the power of 4. Sorry, 3. So that's the question. Well, we have 4 cubed greater than or equal to 3 cubed. Well, that is true because we're taking cubes of 2 numbers. So the bigger the number, bigger the cube of the number. That's fine. And for n equals 4, we have 4 plus 1 cubed, right, is greater than or equal to, of course we're thinking about it, let's write a proper question mark, 3 to the power of 4. Now that's going to be 5 cubed here, and this is 3 to the power of 4. So here 5 cubed is 125, and 3 to the power of 4 is 81. So this is also a tick. So we have now shown case by case, because I had only 4 cases, that this inequality is correct. So that is the proof. So when you have a proof question, just check whether you are given finite number of cases, as for example in this example, which would be 4 numbers, 4 natural numbers, right? So you can just try it out and you can show that the statement given is true for these given cases, all right? So whenever you're going to use proof by exhaustion, you must have finite number of sets. All right. So thank you very much for watching.